So this is the next figure. This is the figure triangle TQR, and point P is on TQ somewhere, point S is on QR somewhere, and they're connected. So angle 1 is equal to angle 2. That means angle TQS or TQR is the same as PRQ. Moreover, QR upon QS is the same as QT upon PR, QT upon PR. So this is the information given to me, and say our task is proving this, that triangle PQS is similar to triangle TQR. And once again, if I write it like this, that means the correspondence is also very, very important. P corresponds to T, Q corresponds to Q, and S corresponds to R. So let's see how we can work this out. The first thing that I should notice is that these two angles are equal to each other. That means the side of the triangle, if I am thinking of the triangle PQR, this side is equal to this side because the angles are equal. That means QP is equal to PR. The moment I do this, I see there is a PR somewhere. Let me write a QP. So now if I look at it, QR is to QS, QR is to QS. That means I'm thinking of these two triangles, QPS, and a bigger triangle QTR. So I see there is a ratio of the sides given. This is side of this triangle and this is the side of the bigger triangle. So I have a ratio given. I look at it, I have another ratio QT, that means the big angle. That means again the big triangle side, and QP, that means the smaller triangle side. These two are equal to each other. That means side and side is definitely kicking in. If I can have the included angle as the same, and it is the same because this angle Q is common to triangle PQS, it is also there in the triangle TQR. So I have a side angle side similarity, therefore proven that triangle PQS is similar to triangle TQR. Now once I have this information, if I put a few numbers here, if I call this 5 and this as 2, and I asked you what is the value of this if this is given as something, that should not be too much of a problem, because once you figure out that the triangles are similar, you can start using all the ratio information. So you have PQ upon TQ is equal to QS upon QR is equal to PS upon TR. Because once I notice this, I can actually create problems around it. Once I have one ratio, this is 5 is to 7, and I said this is 15, how much is this? That should not have been too much of a problem. That is the easy part. The difficult part is spotting the relationship first. So I hope this was easy. So I hope you are getting more and more comfortable with the idea. We'll do a lot more problem solving when we come to the similarities exercise or workshop. But for now, I want to focus on another couple of key results that I can derive from the information that I already have, or think of it as warm up for the next class, just getting the idea started. I have two triangles. I have a triangle A, B, C, and I have a triangle P, Q, R. And I tell you that they are similar to each other, which I know obviously means AB upon PQ is the same as AC upon PR is the same as BC upon QR. That much I can do definitely. But this time I want to think of the area. Area of triangle ABC versus area of the triangle PQR. Is that going to be the same as a ratio of sides or something else? What we'll finally figure out that this ratio is going to be the square of the ratio of sides. So normal result for similarity was AB upon PQ. If I am thinking about the area, this will get squared. That means the ratio of the areas is going to be AB square upon PQ square. And once again, this will easily work as a tool when we start solving problems. But our first problem should be, where did this come from? Because the more I ask this why, better my problem solving analytical skills are going to be. So let's start working on this. I will draw a perpendicular on both the triangles. So this is a 90-degree angle, this is a 90-degree angle, this is the height of the triangle, this is the height of the triangle. Let me call it H1 and let me call this H2. So the area of the first triangle is going to be half base into height into h1. The area of the second triangle is going to be half base into h2. Obviously this half is going to get cancelled, so I remove that. So I am left with area of the triangle is BC into h1, area of the triangle is QR into h2. This much I have. But what relationship do I have about h1 upon h2? So that is the main focus area, because once I figure that out, this will be very, very easy. So let me start thinking of h1 for a minute. And now notice the triangle, and let me call this point x and call this point y. And now notice the triangle ABX and the triangle PQY. Triangle ABX, this angle is equal to this angle. Why? I already know these two big triangles are similar, so I know angle B is equal to angle Q. I have that information. I know this angle is going to be 90 degrees because this is a straight line. This is already 90 degrees. That means this angle is also 90 degrees. That means this angle is also 90 degrees. I have two angles already. I know the third angle will also be equal. So I know this triangle is similar to this triangle. That means triangle ABX is similar to PQY. And now if I think about the height, h1 is going to be AX. So AX, the corresponding height here is going to be h2 or PY. So I am looking at the ratio of AX upon PY or h1 upon h2. This is going to be the same as the ratio of other two corresponding sides. That means this h1 upon h2 is the same as AB upon PQ. And I already know AB upon PQ is the same as BC upon QR. That means h1 upon h2 is equal to AB upon PQ, which is equal to BC upon QR. So I can say h1 upon h2 is the same as BC upon QR. So instead of this, I can write a BC upon QR. And therefore I notice that I get a BC square and the QR square. Once you write it like that, BC upon QR square, that you know that the ratio of the area of the triangles is going to be BC upon QR square. Instead of BC upon QR, you can also write AB upon PQ. That means it is also equal to AB upon PQ square, or it is also equal to AC upon PR square. And there you have it. You have proved it, that if you are thinking of the area of two similar triangles, the ratio of the area is going to be the ratio of the sides squared. It doesn't matter which side, because once you have one ratio, you can connect it to all other sides and you are done. But the area is going to be equal to the square of the ratio of sides, right? So we are going from a simple ratio to the square of it, thinking of the triangle. And another result that I have just now worked with it, we did not pay any attention to it, but that is that h1 upon h2 is also going to be the same as AB upon PQ or AC upon PR or BC upon QR. So I see if the triangles are similar, the heights are also in the same ratio as the sides. And now you can actually extend this idea that here we are talking about a height. If you think of the median, the ratio is going to be the same as the ratio of the sides. If you think of the angle bisector, the ratio of the length of angle bisectors is going to be the same as the ratio of sides. So now I will be able to create a longer or more fruitful relationship, because not only the sides, anything in the linear form, any single dimensional entity, the ratio is going to be the same. But remember, for area, it is going to be squared.